All right, so the next set of notes that we're going to look at is just kind of going back over and revisiting the applications of the derivatives, the things that are going to be so important for the AP, that you really understand what a derivative is, what the rate of change, how do you use the derivative to find it, how do you interpret rates of change, how do you answer questions on the AP. So this is one of those, not necessarily its own section, but it comes right now in section 3.3 because you finally have enough shortcut rules that you can actually do a lot of these problems without having to use the limit definition. So what we're trying to do is to get you to kind of work through and really understand the application, the concept of the rate of change and how to use them for application problems, which are pretty heavy on the AP. Now, when we take a look at the first idea here is that you have to remember that your function represents a quantity. It may be the amount of something, it may be a position function, it may give you a height at a certain time, it may give you an amount that you have at a certain time, but it's basically a quantity. You use the function to find points where at a certain time, which is usually what applications are dealing with, at a certain time you have a certain quantity of a object, whether that is height or position, location left or right of a certain starting point, position up and down of a starting point, or whether it could even just be a quantity of widgets that you have made. At time t, you have X number or Y number of widgets. So the idea is you have to understand what the function gives you, which is, in our math world, a point on the function. And then you have to know that our derivative, the slope of the tangent line, our instantaneous rate of change, our instantaneous change in y over change in x, and understanding the units, which would be the units of y over the units of x. So all of these things are going to be important. And we've started looking at these application problems, but what we really want to do is practice and practice and practice so that the fact that you're going to see a lot of real-world problems on the AP is not going to scare you. Our function, again, could be the position or the velocity or the quantity of anything. It could be the area of a circle, the temperature at a certain time, the amount of rainfall, number of people infected with the disease. Like, for example, we're looking at the Ebola epidemic right now. So we could be looking at a function that describes the number of current cases of people with Ebola. And the idea is that the power of the derivative is going to give us a way to talk about how fast the speed, the velocity that something is changing in a single moment in time. And that's kind of important, like especially right now when we're talking about the Ebola epidemic. It's not so much how many cases we have currently that's important to us, it's how fast the number of cases is changing with respect to time that is kind of what has the epidemiologist worried. All right, so we're going to basically go through this first little section of notes and really talk about the interpretations and what does each thing mean and what is it used for to kind of really get it cemented in your mind. All right, now, so first thing is, this is probably something you saw in pre-calculus. We have the temperature in degrees Fahrenheit of a cold yam. We're going to put it in a hot oven, and we have this function that describes the temperature at a given time. Time is going to be in minutes since the yam was put into the oven. So kind of the first thing, maybe we want to think about what this picture is going to look like for this function, have some idea of what will happen. We have some initial temperature of the yam. So we'll put T sub 0, initial temperature. We like to use that kind of notation for it. And since it's a cold yam, put into a hot oven, we'll kind of say that our hot oven, maybe the temperature of the oven will be up here. So T sub, a lot of times they call this T sub A, but they'll use different letters. But basically this is the ambient temperature of the surrounding medium, which is like room temperature, temperature of an oven, temperature of a refrigerator, wherever you're placing your object. Whereas this is initial temperature of the object. Now what will happen over time, we can sort of reason that we put the cold yam in the oven and that may be initially how fast our temperature is going to change. It may take a little while for the effect of the oven's temperature to start changing the temperature of the yam, but we would assume that maybe so that the temperature of the yam should increase, okay? And initially it'd say that maybe it's probably increasing at an increasing rate because the difference between these two is fairly, you know, big difference, that initially it will start to increase maybe exponentially up to that, and then eventually it will start to level off and reach our curve over here. You know, that could be one option. It could be that it's pretty exponential kind of a growth as we look at it. It may start from here instead of slowly starting out in this idea. It might come in and kind of have the fastest temperature change here at the beginning. We don't really know kind of what the shape of this necessarily is, but we can kind of think about this idea and talk about what's going on, what might be happening at different points in time, what do we know about how fast the temperature is changing, which would be our derivative. All right, so the first question comes along and it says that what is the practical meaning of the equation f of 20 equals 255? All right, so f is our temperature function. Okay, 20 is our time. So the idea here is that are we talking about an interval, an average? Are we talking about at an instant? What are we basically talking about here? Now in AP, you want to kind of really you've got to be referencing a moment in time or an interval of time. So in this, we would say at a time t equal to 20, and you have to always make sure you include units, at time t equal to 20 minutes, then you have to follow it with what are you talking about? What is this 255? That would be the temperature of the yam is 255 degrees Fahrenheit. That the idea is that at some moment in time, at time 0 is when we started recording our temperature, and then somewhere out here, 20 minutes later, and this is going to be measured in minutes, at time 20 minutes, we are going to have a 255 degree Fahrenheit temperature of this graph. All right, and so that's our interpretation. So we understand that the original function, because it's a quantity function, our quantity is the temperature. Our unit in the x-axis is going to be the time in minutes, and our unit for the y-axis is going to be the temperature in degrees Fahrenheit. All right, now talking about the sign of the derivative. Okay, now remember that the sign of the derivative is the slope of the curve that you're looking at. We have this function that is the temperature function. What you're basically asking yourself here, if I want to know the sign of f of t, I'm asking, is f of t, your temperature, your quantity function, is f of t increasing or decreasing? And the answer to that question is what's going to tell us what about the sign. We know that if your function f of t is increasing, then the derivative f prime of t is positive. Right? And we know that if your original function, your quantity function f of t is decreasing, then your derivative, your slope of your tangent lines, f prime of t, is negative. So that's kind of the background to the question. And now in our real life scenario, we put the cold jam into the oven. The oven's hot, so the temperature of the yam should only increase from its minimum, which was when you put it in. So you can reasonably say with our common sense, we're going to use our common sense, not necessarily our book smarts here. Our common sense tells us that the yam's temperature is going to increase the entire time up to this oven temperature. So in terms of the sign of our derivative, I would say that the sign is going to be positive. F prime of t is positive, and our reason why would be because f of t increases on the interval of interest that we're looking at. Okay, we have to remember that when we are justifying anything in the AP class, that we are using calculus to justify. All right, now we come down here and let's talk about units. It's always important when we start looking at things to be thinking about units. When I was up here and I'm looking at this idea, Our F of T, right, which is our temperature, is in degrees Fahrenheit. Our little t is our time, which is in minutes. So we've already identified units for our x-axis and units for our y-axis as well. But now remember that we're looking at the units of the derivative at time equal to 20. And so our units, if you remember, this is the slope of the tangent line, which is a change in y over a change in x, would be change in temperature over change in time. So the degree, the units of this are going to be degrees Fahrenheit per minute. That's always a fairly easy thing to come up with, but very important. They're going to be looking for you to always have a unit when you write down your f prime of 20. All right, and then we get to what is the practical meaning of our statement f prime of 20 equals 2. Do not tell me or tell the AP reader that the practical meaning is that the slope of the tangent line at time equal to 20 is going to be 2 degrees Fahrenheit per minute, because they're not asking. The slope of the tangent line is a math meaning. We're talking about real world meaning. And we've talked about this before, this interpretation of slope. You have to always give me the when. So we would be at t equal to 20 minutes. Okay, so this is my when. Then you always follow that with what quantity is changing. The quantity that's changing is the temperature. So we would say the temperature of the yam. Okay, so that's our what in our description, temperature of the yam. Then we follow that with what is the temperature of the yam doing? Is it increasing or is it decreasing? I look at my derivative and I notice that the slope that I'm being given is a positive slope. So because I know that the derivative at 20 is positive, I know that the temperature of the yam, the original function, the quantity must be increasing. So we use the fact that we have a positive slope to say what the actual temperature is doing. It's increasing, okay, so it's when. What are we talking about? What is it doing? What is the action, I guess you would say? Is it going up, down, or staying constant, which is pretty much what your choices are, up, down, staying constant. It's increasing at, okay, so now we have to figure out, now we got to get the actual slope in, because obviously we have a derivative, we're trying to interpret it. It's increasing at 2 what? What are my units? 2 degrees Fahrenheit per minute. Okay, now the key here, and this is the kind of, so we have when, we have the what's it doing, how much, and then you always follow that with your units. And if you have those 5 parts when you are interpreting your instantaneous or average rate of change, it doesn't really matter, the when, the what, which way, how much, and what your units are, you will always get full credit for this practical meaning. And you do want to make sure you get into the habit of that. So if you did not do this for, like in worksheet 3.2, we had several times, anytime you find an average rate of change or anytime you find an instantaneous rate of change using the derivative, you want to get into the habit of writing this sentence, especially if it's a real world problem. All right, so let's look at another example. So in example number 2, we have an ice cream company, and the ice cream company knows that its cost in dollars to produce Q quarts of cookie dough is going to be a function of Q. Okay, so your cost is a function of your quarts. You have more quarts, your cost will be higher, typically. All right, so we have cost is a function of the quantity of the quarts of cookie dough. So our quote-unquote quantity function is going to be C. This is what is changing. This is our quantity, our amount that we're looking at. All right, so we're looking at our f of 200. We're given f of 200 is 70, and we're like, what are the units of 200? Well, recognize that 200, when you're looking at this, is this portion of the formula. It is the quarts of cookie dough. So we have 200 quarts of cookie dough. Cookie dough ice cream. I will abbreviate here. Oops, can't spell. All right, and then we say, well, what are the units of 70? Since the F of 200 equals 70, this is the output, this is the quantity or the amount, which in this problem is referring to the cost in dollars. So the units of the 70 is going to be your dollars because this is referring to the cost of your ice cream. So if I'm interpreting what this is saying at a production level, okay, or some name you want to give this production level of 200 quarts, the cost to produce is $70. All right. So it's an interpretation. You got to know this is the when in this, and this is what your quantity is because you're doing the F of the quantity function. All right, and then we come down and now we're looking at F prime of 200 equals 3. Now again, the 200, regardless of what we're looking at, the input doesn't change. The input is still talking about your quarts of ice cream. So we have 200 quarts of your cookie dough ice cream. That would be our units here. And we want to know what are the units of 3. And this is where it's really understanding the derivative and what it's giving us. The derivative is the slope. The slope is your change in y over change in x. Your change in quantity over change in quote-unquote time, or your when, change in when. So here, your change in y over your change in x, or your change in c over change in q, is going to be dollars per quarts of cookie dough. And so this idea is, what does it cost per quart of cookie dough to produce? That's going to be important. If you're taking the Econ Personal Finance class, this is the idea that we're looking at, this idea that you have a idea of a marginal cost, that it is the cost of one item, not the cost of multiple items, all right? And so what is this equation telling you? Again, we're going to go back to our interpretation. We have to do the when, okay? So when 200 quarts of your cookie dough ice cream are produced, the when, all right, so we have the when. Now we need the what. What's changing because of this rate of change? What's changing is your cost. The cost of producing the ice cream is, now what is it doing? Is it going up or is it going down? The cost is going up because it's a positive number, positive slope, so it's increasing. At $3 per quart of ice cream. Now remember this idea, and this is kind of why we look at this idea of marginal cost, is that at 200 quarts, to produce the next quart is going to cost me an extra $3. So that is kind of your instantaneous rate of change. That does not have to be the cost per quart, your marginal cost, at different places in time. Maybe it costs less after I'm on 200 quarts because I've already got my equipment in place, so it doesn't cost me that much. But maybe back when I had 100 quarts and I want to look at the cost of producing another quart when I have 100 quarts currently being produced, maybe that's a lot more because maybe once I get to 100 quarts, I have to buy new machinery. So maybe then dividing the cost of new equipment into the idea in order to make more of them, maybe my slope is higher at that point in time. So again, I'm stressing to you that in order to get credit for an interpretation of a derivative, you have to have when, you have to have what, you have to have which way, how much, your units, and if you have those 5 things, you will get your credit. All right, so now let's take a look at example 3. All right, so in example 3, what we have here is now we're having a function that's going to give us the number of centimeters of rainfall that has fallen since midnight. and T is going to be our time in hours. So we're going to interpret each of these in practical terms, and we're going to give units. All right, so I'll start with the units of each. So the 10 here, okay, F of T, time in hours, so T is referring to 10 hours there, and our 3.1, that's your output, is going to refer to your centimeters of rainfall. Okay, so we can get our units fairly easy. This is the quantity function. So what is our interpretation of this? Our interpretation is when, okay, after 10 hours have passed. Now a lot of times we're going to put this in common sense. After 10 hours have passed since midnight, what time are we? So we would say at 10 a.m., because 10 hours have passed, that's your when, the amount of rainfall fallen since midnight, the what, is 3.1 centimeters. So the when and the what, because that's a quantity function. All right, and then now we're going to play around with you just a little bit and say, oh, now I have f to the negative 1 of 10 equals 16. Now this goes back to Algebra 2. What does f to the negative 1 mean? What do we read that as? This is actually read as f inverse. Okay, and now let's remind ourselves, what does an inverse function do? An inverse function will switch x and y. Switch your inputs and your outputs. So now when I'm looking at this 10, even though these look very similar to each other, you'll have to recognize, okay, wait a minute. The 10 here is really used to be the output over on the quantity function. So the 10 here is referring to 10 centimeters of rainfall. And the 16 is now going to be the 16 hours. Right? And so now in this function, because we've switched x and y, what we're basically doing here is we're saying based on the rainfall, how many hours have passed. So our when is when 10 centimeters of rainfall has fallen since midnight, it will be 16 hours past midnight. What is 16 hours past midnight? Well, that would be when. So 12 hours would be at noon. Another 4 hours past that, it will be 4 p.m. All right, so we're going to put this in terms of context. Now, we can have all sorts of discussions about, the one's an independent variable, one's a dependent variable. Does the output depend on the input? It doesn't really matter in this situation. You just have to interpret what they're actually saying in the function. The when and then what quantity, and because I switched x and y, the when is when you've collected rainfall, and the quantity is you're looking at what time it is. Right? Now we come down here to C. Now we have f prime of 8 equals 0.4. So f prime, that's our derivative. Okay? F prime. So we know we're talking about our derivative. So the 8 is going to be the same input it was in the original function. So that's going to be 8 hours past midnight. I guess technically in all of these I should be doing hours past midnight, since that's the way they defined it. And I'll fix it up here, 10 hours past midnight. All right, so we have 8 hours past midnight, and remember that your derivative is your slope, your change in y over your change in x. So our quantity was centimeters of rainfall. So now this 0.4 is a change in y over change in x, so it's going to be our centimeters of rainfall per hour past midnight. All right, so it's our change in y over our change in x. All right, and then here we are, we're going to interpret this. Our interpretation, our when, at 8 a.m., our what, our rainfall, amount of rainfall. And what is our amount of rainfall doing? Is it increasing or decreasing at this point? We have a slope that is positive, so the amount of rainfall is increasing at 0.4 centimeters per hour past midnight. Okay, so we have our when, our what, our which way, how much, and our units. Okay, so we want to be very, very careful and make sure that when we are interpreting a slope, we include these 5 things. Notice when I'm interpreting just a quantity, I just need to know the when and how much. So that's a little bit easier, but slopes have more things going on. All right, now we take a look at this. You're like, oh shoot, this has the derivative of the inverse function, the derivative of the inverse function. And that will come up because we do have a lot of times we're interested in the derivative of the inverse function. What happens when we do the derivative of the inverse function? Now, a couple of things. First, let's remember that the input would be the same as the input to the inverse function. Our input to the inverse function is our centimeters of rainfall. So our units here, we would have centimeters of rainfall. Okay, and now remember that this is a derivative, so it is a slope. But remember now, when we do our change in y over change in x, make sure you're doing change in y for the inverse. So in this case, our units are not going to be centimeters of rainfall per hour past midnight. Your units are going to be 2 hours past midnight per centimeter of rainfall, because we have switched our x and our y. So when you switch x and y, your slopes become reciprocals of each other. So that's going to be an important concept. It's going to come up a little bit later when we start doing the shortcut rules for derivatives of inverses. All right? So now let's interpret this slope. So again, we have to do the when, but now remember the when is referring to this 5. So when 5 centimeters of rainfall has fallen, okay, our what are we changing here? Let's come back up here to our quantity. We were putting in centimeters of rainfall. Our quantity was the hours past midnight, the time. So our what, in this case, is going to be the time. So when 5 centimeters of rainfall has fallen, the time past midnight, the hours past midnight, let's do hours. The hours past midnight is doing what? Increasing or decreasing? Is increasing at how much? 2 hours past midnight per centimeter of rainfall. Now, I will say that mathematically this is our interpretation, but this interpretation really doesn't make a lot of sense, because think about what we're saying here. We're saying that once I know that my little rain collector has 5 centimeters of rain in it, I am basically saying time is passing at a rate of 2 hours per centimeter, which doesn't really make a whole lot of real world sense. And so we get that. So there are some of these things that we can write down what they mean mathematically, but they may not really have a great real world context. But what you are noticing and hopefully looking at, that you don't necessarily care so much about that. When you're interpreting this, you want to make sure that you're putting it in terms of your when, your what, which way, how much, and your units. You're doing exactly the same thing, and you have to kind of really have it straight in your head. Now, yes, in this example, that's not the best example because the rainfall collecting is not really changing how fast time is going, but it is this idea of being able to interpret it and write it down. All right. Now, a lot of times when we're looking at these interpretations, we do use the word instantaneous, but it does not have to be instantaneous in reference to time. Okay. Basically, a lot of times we really just say this is how fast the quantity is changing based on some other input variable. So it is your interest rate per dollar, okay, amount that you have in the account. You could have a your amount of work that you have completed per hour, and that would be a time. But you could also be looking at how much time per job that it's going to take. There are different types of slopes out there. Slopes are instantaneous rates of change when we're looking at a function and seeing what the slope of the tangent line is at that moment. And it's just change in y over change in x. All right, we're going to finish this little section of this out with one example just to kind of show you a different word where it's not always with respect to time. So we have a circle, and the radius of the circle is increasing. So we have a circle, we have a radius that over time is growing and getting bigger. Maybe I am pouring liquid out of a pitcher onto the ground, and it's forming a circle, and the more liquid I pour, the larger the circle becomes. Okay? And so maybe we're interested in how fast is the area of the circle changing with respect to the radius. Okay, so the first thing that I'm going to do here is, because I am looking for a speed, how fast. So I'm basically looking for, and this is where we're going to start using our derivative notation, our d something with respect to something else. We're going to say we want to find the derivative of the area, because that's a speed, a rate of change. How fast, rate of change. We're looking for a rate of change in what? The area, but we're looking at it with respect to the radius. So this is dA, dr. Now, this is a very, very important concept. We're trying to take the derivative of the area with respect to the radius. We may be interested later on in trying to figure out, well, how is the area changing with respect to time and how is the radius changing with respect to time? Those would be different rates of change. But in this problem, we're looking at how fast the area is changing with respect to the radius. Now, because I'm looking at it in this idea, what I know is that the function that I'm going to start with, I need my area as a function of the radius. And so with this, we know that the formula, our quote-unquote quantity function that we're going to be looking at, is going to be obviously area equals pi r squared. Area as a function of the radius. So that's going to be my quantity function. So I'm going to start with the quantity function. Now I'm interested in how fast the area is changing. So I'm interested in the derivative of this quantity function. So now I'm going to find the derivative of the area with respect to r, okay, which is nothing more than a power function, pi times my variable squared. So I multiply my power times my coefficient, 2 pi, write my variable down, and subtract 1 from my exponent. So this derivative is going to be 2 pi r. And note that is not a coincidence that that happens to also be the formula for the circumference. But what we're looking at here now is, so we have our formula for our derivative. We could think of this as kind of putting it back in our function notation. This is our a as a function of r. This is our a prime as a function of r. That the derivative, the slope of how fast the area is changing given a certain radius. Now, we want to determine how fast the area is changing when the radius is 5 inches. So over here in part A, I would say I'm basically going, well, do I know what the radius is? The radius is 5 inches. So when r equals 5, my a prime of 5, my derivative, is going to equal, plug in your 5, and you're going to get 10 pi. All right? Now, an alternate way to notate this, and I'm going to come back and do units here in a second, that my dA, dr, and this is where you have to be careful. If I want to plug something in, there's not really that little function notation to plug in. This is our evaluate bar. You've seen that when you do your n-derive if you have the newer calculator. So we're going to take this derivative, the derivative a with respect to r, and we're going to evaluate it at r equal to 5. This means the same thing as a prime of 5. And so we would plug it in and get our 10 pi. So these are two ways to discuss that derivative. All right? So that's kind of how I find the answer. But now we also want to make sure that we interpret the answer, that we know what we're doing, we're using good notation, we're labeling, we're going to answer the actual question. So the answer to the actual question is when the radius is 5 inches, okay, so those are my units right here, this is inches. The what, the area, the quantity that's changing is it increasing or decreasing? Positive number, increasing at 10 pi. Now let's think about our units of area. If I come back up here, the radius is in inches, so area is going to be in the units of inches squared, okay? And now my derivative is going to be my inches squared, my area, square inches, per change in x, change in y, over change in x, per inch. And we'll say per inch, radius inch if you want to know that these are two different things. This is your square inches, your area that's changing per inch, square inches per inch. Don't simplify it, just write change in y unit per change in x unit. All right? So again, the when the radius is 5 inches, the what, the area, is doing what? Increasing. How much? At 10 pi, and my units, square inches per inch. All right? The answer to B in this problem, all we're doing is changing it to 10 inches. So when r equals 10, our notation, a prime of 10, we would plug in our 10 into our derivative formula, which would give me 20 pi. And another way, if I use the Leibniz notation, my dA dr evaluated when r equals 5 would be 20 pi. So my interpretation on that one would be when the radius is 10 inches, the area is increasing at 20 pi square inches per inch. Which basically is saying for every inch the radius increases, the area increases 20 pi square inches. Right? But this is how they're going to want you to write that interpretation. All right? And then the next part of this question says, how fast is the circumference changing at these times? So now let's think about this. First, at these times is when the radius equals 5 and when the radius equals 10. So the time is not a time as in minutes, it's a time as in a reference point in time when the radius is 5 and 10 inches. So we're going to do the very same thing. We first need to have a quantity function. Our quantity function, our circumference, is 2 pi r. Okay, so there's my quantity. We're interested in how fast the circumference is changing. So how fast is a rate of change? And that rate of change is going to be the change in the circumference with respect to the radius. So I'm looking for dc dr. So my derivative that I'm going to find, my c prime of r, okay, and again, that's kind of thinking of this in function notation as c of r. C prime of r, also known as dc dr, is going to be equal to the derivative of this, which is a power function with power of 1 times 2 pi, and then r to the 1 minus 1, which is r to the 0, and it's going to go away. So we end up with a constant derivative for the circumference function, right? And that should make sense because this is linear. It's a linear, circumference is a linear function of the slope, or of the radius, and 2 pi is your slope, and so the slope, it always increases. For every inch the radius increases, the circumference increases by 2 pi. So that should make sense to us. Now, if I were to ask you for A, when r equals to 5, because my c prime of r was constant, c prime of 5 is going to be, hey, 2 pi. For B, when r equals 10, c prime of 10, because it's constant, it's the same everywhere, is going to be 2 pi. Right? What are our units going to be? Right? Well, let's put the other notation in and then we'll stick our units in. So we would also write this as dc dr evaluated at r equal to 5 would be 2 pi, or dc dr evaluated when r equals 10 is 2 pi. Now, just as a comment about this, that one way that you could also do this is you always want to reference when. So you could up here just go c prime of 5 equals 2 pi. Okay? Or you could say along the lines of when r equals 5, c prime of r equals 2 pi. So you could kind of do this kind of idea. I don't really like that as much. I much prefer that if you're going to do the notation, you do one of these two if you're referencing a specific moment in time. All right, now let's do our interpretations. So for the first one, we would say when the radius is 5 inches, the what, circumference, is, how is it changing, increasing or decreasing? Positive derivative, so is increasing by 2 pi. Now be careful, this is a circumference. What are the units of circumference? It's basically the same units as your radius. So it's increasing by 2 pi inches per radius inch, per inch. And I know that looks weird, inches per inch, but that's what the units are. Your change in your circumference inches per change in your radius inches. And that's not coincidental that you have inches per inch, and that's a constant because 2 pi is the same no matter where you are. All right, and then over here, when the radius, can I just say the same thing would be true, just change this to 10, and then you could say the same thing. All right, so let's stop that video. We'll stop right here. So this was just an idea, trying to get you into this idea that you really have to work on your interpretation, that they are really, really being very sticklers for your notation and your interpretation when you're doing rates of change problems.